We had that problem.
And you get everything here.
Yeah, like
I'm not sure if I'll be here next week.
after my freshman year, everyone graduated, so then it was a bunch of sophomores.
I might stay in July.
What?
Well, then, like,
I
you
have no
guys
idea.
run for office.
I'm already a
Come
part
get
of
pizza.
Junior Clubs.
I didn't know. I had zero. This week we did the connection.
Do you have a meeting every week? Every other week?
Pretty chill. Not usually. We have geo.
How did that go?
And marshmallows. We did like a companion drop.
Dope. I'm pretty fun right here.
I feel like you should also do a math meeting.
I would come to Canyon for your
I feel like I've heard that I haven't heard anything about them, but they sound scary.
We just
I
chill,
want
have a
to
good
go for
time,
math.
tell some jokes, and
That sounds awful.
It's my night.
I know.
Tell jokes.
I feel like you've never seen
yeah,
it.
it's very laid back. We just have a good time.
Yeah.
So highly recommend.
I was just like a new experience.
Next time I think we're doing a Kahoot for our December one because it's like we're doing food next. There's like a periodic table trivia. Kahoot.
Oh,
We're still nerds. Like we're still nerds.
I mean, I've kind of died to Kahoots from work, but I think I can manage it on
Work at the wellness home?
No. RAs do so many Kahoots.
Oh, that's true. But this will be a fun.
Well, anyway, please just to read with this one. This will be the key for the words.
Next semester we're kind of like blow up, you know. So big plans.
I think it is.
I'm secretary.
So sure, you are confident that no one wants hidden identity.
Okay, no.
Don't complain for me to disclose it.
Oh, wait.
Thank you.
The main thing here is to remember that we all fail.
Another drug use a little information.
Tell my dad.
Very easy answers. Very easy answers.
Here we just go.
So there was suggestion to fill the values of annihilation operator, right? And the annihilation gets elements above main diagonal with progression of square root of index starting from 1. And for the creation operator, it's symmetric in respect to the main diagonal. So it's square roots of n on the subdiagonal. 10 points. Right? I think the only error can be swapping their order, but do not withdraw all points if there are errors. Withdraw partial. So another question is verbal explanation. I think you all did it right. Just look for words that zeros on the diagonal, language like subdiagonal, square roots, above or below, things like that. Give credit for it's like middle school composition. Where do you see zeros? Then the matrix elements of position, momentum, position squared, momentum squared. So during the class we did have the definition of position operator as summation of correlation and annihilation with a factor up front, right? So you keep the factor up front and then add together the square root of 1 above and below, square root of 2 above and below, and it will be sufficient. If it is momentum, then above main diagonal you put minuses, right? And there will be another factor up front. So total for this question is like 30 points and just distributed evenly between all assignments, like 6 points per operator. For x squared, if you see this point and even if there is no matrix, give partial credit. If you see an attempt to convert it in a matrix form, be generous. Same with momentum. So potential energy is position squared with a factor, so it will be the same as position squared. Momentum squared with kinetic energy with the momentum squared with a factor, so it's the same as here. And if one needs total energy, one adds together kinetic and potential, and you identify that the factor up front here is, if one plays with this mass, constant, and frequency, factor up front will be the same if you process this factor in terms of Planck constant. And the first and last cancel, and two middle terms stay. So it will be A dagger, A. If you see expression like this, give full credit even without any operators. If you see either matrix or through commutation, you see this expression, add a couple of points. And some of you may have skipped this thing and just put a matrix for this h bar omega up front and then just main diagonal with 1/2, 3/2, 5/2. This also a legitimate answer. Okay, next. So this commutation between A and A dagger were already provided, right? You didn't derive them, you just used them. And the question was to practice commutation between Hamiltonian and annihilation operator, right? So I do not have a significant speech defect. What you will hear right now is just my attempt to pronounce what is written. A minus A. So you have A dagger A minus A dagger A, right? Because you just open this this bracket. Right? And if you open, you see that dagger is placed at a different part of this expression. And what is the meaning of these commutation relations? It means that as soon as you see A dagger, you can move this minus A dagger A on the other side and replace it by A dagger A plus 1. So you do it here. It will be probably the only memory about the class. What was physical chemistry about? The instructor was telling 5-6 times A in continuous. So why do I need to do this plug-in? Because I really inclined, I want to subtract these two operators from each other, but if the order of operators is not the same, I'm not allowed to. Because they are not equal. Although they, how to say, we all here are in chemistry department, right? But there are isomers, same chemical composition, but different structure. So composition of this operator is the same. 2A, 1A dagger. But since they are in a different structure, they are not equivalent. And there are tricks that may bring them to the same form. So A with dagger should be first, and here it is not first. In order to make it first, in order to swap the order, we pay a price, we add 1. Okay? So then it will be A dagger AA minus A dagger AA minus A. So this A comes from this plus 1. And then the first two terms cancel, and you get minus A per omega A. So commutation between Hamiltonian and annihilation operator gives annihilation operator itself. If there are 40 points, you just put 20 for this and 20 for another one. The goal of this exercise is not only to accumulate points in the homework. It will be used several times in the rest of the class material. So, why do we need to explore computation of some of selected operator and Hamiltonian? What are the reasons? If you scroll back our memories, if there are some records about this class, in which cases we may want to explore commutation of an operator with Hamiltonian. Two situations. And they're basically connected. How many ways to predict future do you know? 3. Yes, I know 3. And there is a 4th way, which is not quite predicting future, it's more predicting observables, which starts with letter H. Equation of motion by
The harmonic oscillator.
no, Heisenberg. Oh, it's more in general, right? So if you need to find how operator or how observable evolves in time, you do compute this observable with Hamiltonian. So if we need to find how this, if there would be observable corresponding to this A, we may want to compute it with Hamiltonian. Another thing, if commutation of an operator with Hamiltonian would be 0, it would mean that observable corresponding to this operator doesn't change in time. But we do not get 0. It means that if we ever need to explore it, it will be changing in time, will be some dynamic. So, but one reproduces the operator itself by doing it. Anything else? Were there more questions in the homework?
5 and 6.
Can I see?
Or those that extra?
6 and 5 was not.
5 should also be extra.
Well, just be generous. So what the extra credit was about?
It's using, I think it was using the other operators that you found, or not the operators, but the.
Okay, yeah. Just if you see something, give something. And please accumulate all points and put them on the front top page.
Should we make the last problem?
So is it just out of the 90?
Uh,
Because it was 10, 10, 30, and 40.
I miscounted some.
What were the other problems?
What's it? 90?
There's
Because-
two more
because-
problems.
But the
Problem
6 was
5.
after.
Yeah.
It was 5.
5 must have been worth 10
Third,
points.
these are 30 points. And
And
4s are 40. 70, 80, 90, 5.
Okay.
Just like 100.
I was designing to have 100.
Okay.
Oh, no, I'm going to see it.
I was just showing her.
Oh, okay. Thank you. Come on, you don't need an instructor, we just teach each other. Thank you. Oh,
Yeah, very good.
you're a good grader.
God,
Well,
you're
what
great.
changed from the first time?
Oh. Well, his answers were right, Amelia.
All right. Oh.
Aggressive. Man, I did not know if you.
If okay, very good, very good. No time for project right now. I saw some suggestions and I did publish online our last lab, which is not interested for everyone if you look for this 2 hours, but last 10 minutes are useful. I need to send a link, but if you look online for the channel, it will be like fast. So last time when there was no time for this verbal things, I will run a marathon. And there will be review, brief overview of the expected result, and then a lot of math that I will scramble together and invite you to just have a net to understand. So last time we did recursion because we are looking for eigenstates of annihilation operator. And we identified that if recursion is practiced, and then we wanted to normalize this state, then in order to have normalization 1, the coefficient should be eigenvalue of this annihilation operator in the power of exponential squared and divided by 2. And we also mentioned that it was Poissonian distribution. Also, there is nothing that forbids us to combine this eigenvalue with accumulation of phase coming from eigenstate in the power n. And then if you do this trick, because eigenstate n will correspond to e to the power minus I n omega t. But then one can, and mu also comes in power n. So why don't we merge them together and tell that mu times e minus I omega t will be a new time-dependent eigenvalue of annihilation operator. Okay, this was a review. If you have strengths to keep something in memory, then you may want to keep this in memory. It's not one-time exercise. I will return to it. Who needs it? Morgan needs it. For the project that you have chosen, you will have overlapping several harmonic oscillators, and in them, so this is a physical, chemical, scientific, experimental situation when such Gaussian states are created on a true experiment. Suppose you have a molecule, metal organic complex or whatever. It has several potential energy surfaces, at least ground and excited, maybe a few more. Those potential energy surfaces often have different equilibrium distance. If you excite it, changes equilibrium distance. Maybe curvature, but sometimes curvature is the same. So one can consider this parabolas. If system is originally in ground state electronically and from vibration point of view, it will be in this Gaussian distribution. But if one applies a resonant laser excitation promoting it higher up to next potential energy surface, electronic state changes, but nuclear state keeps the same, and the shape of the distribution stays the same. So you promote Gaussian wave packet from lower potential energy surface to higher potential energy surface. And here it will be still Gaussian, but it will be far from equilibrium. So it will be exactly this coherent state that will start to oscillate. Okay. And we do want to see how it oscillates. Main beneficiary is model. Okay. So it should be number 34 in the, which means we are one lecture ahead of last year. We were behind, now we are back. You already know this thing. It is what you got in the. Just want to enhance the screen. It's more important. So, Jung was partially presenting to us, right? And you all were practicing it in a week and a half ago. Not last Wednesday, but previous Wednesday, where we explored how the width changes, and also if you put either positional momentum not in the equilibrium, it oscillates, right? So, if the width of the wave packet was chosen identical to the one for the ground state, then width was not changing. It's your achievement, your discovery. And then it was keeping the same shape, but was translating forward and backwards in a sinusoidal way, right? Or cosinusoidal. So it keeps the form of Gaussian exponential, but the center deforms oscillation. Yes, you are looking in the right direction on the whiteboard. So gamma, rho, omega, and u. I was following a specific book, and if time allows, I will print and share a page. And I just didn't want to clash with authors. And instead of letter mu in everything we did before, they used the letter gamma. So it is eigenvalue of the annihilation operator. Wherever is gamma, we assume u. And for practical reason, they wanted to split phase on the initial phase factor and accumulation phase. Typically, we just write omega t, but if you are not satisfied with what I show, I can, it's basically copied from the origin. I'm not designing myself, but following. So if we arrive to this expression, probability distribution as Gaussian function with the center of Gaussian coherently oscillating, it will be great success. So it's a task for 20 minutes. Now, you can take a nap, fall asleep and relax. I will try to make a logical connection between what we did before and this final expression. The meaning is just oscillates. Oscillator oscillates, but it has shape. But if shape is chosen right, it doesn't change. Unlike free space. In free space, shape expands. In the Gaussian, if it is chosen right, it will stay same. Okay. Now, if some of you are following, I will tell when it will be important thing to record or to focus. Amount of slides is bigger than it's possible to record. Here is general philosophy of our exercise that I will do for next whatever 15 minutes. You all are agreeing, at least no one was publicly opposing the idea of stick man climbing the ladder and trying to climb lower than the ground state. Right? So we applied annihilation operator to the ground state, and then which must be 0. And it was a differential equation to find the ground state. Now we are taking this previous exercise as the reference point and expand for it. We already know a lot about eigenstate of annihilation operator. You can write it down as expansion. But let's look on it, return partially back into a differential representation continuous. Eigenstate equation for annihilation operator. So unknown function, operator, eigenvalue. And you already know what comes up. If we have, instead of 0, we do have the function itself. Okay? So it should be connected to what we did before, but in the coordinate space. And differential equation of this construction should be available to our mathematical strengths. Annihilation operator is just summation of position and derivative over space, right? And there is just linear. So it's first order linear differential equation that should be doable in class within limits. So here is just how gamma nu is replaced with gamma. This is what we already know how to replace annihilation operator with differential operators. So it is a definition, 1 over square root of mass frequency plus constant, and only nothing here. And if one carefully processes it, then one can express it in the form of x, ddx, and all constants can be combined, like one constant over mass and frequency, into this sigma. And if I'm not inviting you to do it, but if someone is very curious and will look back in previous lecture material, one would recognize that it is the width of ground state harmonic oscillator. So we replace annihilation operator with this combination of differential operators. I think I have the same slide with a better typing, but let's do it right away. So position and derivative factor, unknown function. How to solve this equation? One can symbolically divide left and right part by psi, and symbolically multiply left and right by derivative of independent variable. Then we are getting these phase factors in the denominator and numerator. Here it was x, and we need to integrate x dx. Right? Here we have d psi over psi. Right? Here we have just integral over dx. So basically, the equation is taken. Right? So Morgan will help us to take integral of x dx. What is integral of x dx?
1.
Oh. No, I like this logic. If in all educational processes, if the questions are designed in the right way, the answer should be either 0 or 1.
Yeah, that's
If the answer is not 0 or 1, it's not useful for multiple choice, and it's a problem of instructor. So x dx.
X squared.
Okay, over 2. Yeah. And d psi over psi, we all can read. Integral.
Natural ones.
Yeah, good. And I know it myself, I will not ask anyone. Just text. So if we divide each term by sigma, then will be x squared over 4 sigma squared. Here natural log. Here the gamma, which is eigenvalue, over width times x. And here I put psi naught in the denominator because when you solve differential equations, you need to have a free factor to like, scale it and match initial conditions. So basically, there will be nothing new. I will just trying to be a jongler of to manipulate with this equation to get to the final equation that you already saw. So from here, we need to get two things. That eigenstate of annihilation operator will have a Gaussian shape. And second, that expectation value, eigenvalue will perform coherent oscillations in a cosine wave. So if you move everything with psi to the left, everything with x to the right, we can take exponential. So some initial constant exponential minus x squared with some sigma, gamma over sigma times x. This is already similar to Gaussian wave function, right? So you have x squared to the second power, but we do need x minus x naught squared, right? Which thoughts visit you when you look on this equation? It's 10 minutes and I'm free. Do you have any other thoughts? Can we add and can you consider it as like a squared, or a will be like x, 2ab, or a will be x, plus b squared, and then minus b squared, right? And then one can identify full square. It is basically what I'm going to do. And also, to jump right into the goal, we will need to find absolute value square, probability distribution instead of wave function. So this is just a little dictionary of stuff there, of what is in the text by Schatz and Ragnar. So we already agreed, and major practical use of our previous lecture was to agree with the following idea. Eigenvalue of annihilation operator is a complex number that oscillates cyclically, right? And previously we got it through this expansion, through eigenstate expansion. Now we can just write this initial value times imaginary exponential imaginary unit and phase accumulation. And just to match the text, instead of omega t, we put here initial phase, because we do not know where it did start. Right? So if you start not at time 0, but time minus 50 seconds. Okay. So now, if we are looking on the probability distribution, we are multiplying these two exponentials by themselves. Note that if it is wave function star, then anything that is potentially complex should also have a star. So I gamma, which is considered as eigenvalue of annihilation a thing that accumulates phase. And if you take conjugate, it means we need to swap sign minus. So these two blocks are identical except that this gamma star is replaced by this thing, minus I accumulation phase. So we multiply two exponentials. In each exponential, there are two terms. First term is x squared with factors. They just add together instead of 1 over 4, it will be 1 over 2. And there are two terms that do not coincide. They differ by gamma and gamma star. So this gamma and gamma star are complex exponentials that accumulate phase with time. But they are accumulating in the opposite direction. One is e to the power I omega t, another is I to the power different star, like plus omega t and minus omega t. What do we get from our old body? If we add together e I omega t plus e minus I omega t. I thought it's like, I know the answer, but I will not tell anyone. Huh? Okay. One imaginary exponential is expanded into what? Real and imaginary. Real will be start with letter C, and imaginary start with letter S, sine. Okay. And if you add together, sines will cancel, and cosines will add. It will be 2 cosine omega t. So here, from adding together these two eigenvalues of annihilation of array that dynamically accumulate phase in the opposite directions, we are getting cosine. And we are getting rid of any imaginary things. Our probability distribution will be fully real, exponential of real array. And here we'll be oscillating exponential. So we are coming closer. You already see hints. It will be Gaussian function, and somewhere in the power there will be oscillating cosine. 5 minutes. Easy. Okay. You already know cosine. I just do not want to waste your time and my time on. No, generally I want to waste it, but not very much. We do not have time for normalization factors. We already know how to deal with them. So everything except normalization for this probability distribution will be x squared. We can put 1/2 out of the brackets, x squared over sigma, and then x over sigma. This 2 comes from Euler. Gamma naught was initial, and this cosine also comes from Euler. So let's consider it as a squared minus 2ab, and then we need to add and subtract b squared, because playing with full square is always very appetizing, and it's easier to analyze and interpret. And then b is this 2 gamma naught cosine blah blah blah. This frequency of the oscillator. And sigma is width of width to length. Okay. Comparing from the previous year, this morning I typed one equation. Last year it was calligraphy, it's not easy. So if we practice combination of full square, a minus b squared, and then we have the b squared term. But we do not care about it because we can assign it to the normalization and tell that when it will be time, when we will be solving properties about oscillating width of the wave packet, we can carefully look on it. And by the way, the sine square of omega t will, if you apply equations of trigonometry, you will see that this function oscillates with 2 omega, as was prompted to all of us by Amelia without any math. So width will oscillate with 2 omega. But now let's forget about it and focus on this term. So we have exponential, this thing. If we call this 2, what else should we do? We can multiply and divide this term by sigma. And then 1 over sigma can be taken out of bracket, right? And then our x naught as function of t will be defined as 2 sigma gamma naught cosine omega t. And then if you take carefully process the normalization, it should have this should be normalized as it should. And here we will get, we already are getting Gaussian shape. But the center of this Gaussian shape is not static. It oscillates as a cosine. And depending on the initial condition, we can start it either to the left, to the right, but it will be a general solution. So what did we get? We get a legitimate solution of time-dependent Schrödinger equation for harmonic oscillator. Why it is important? It's something that we can do analytically with pen and paper. On one hand, it just pleases mathematical ego of some of us, if any of us have. Second, it is practically realizable. One can do it with unprobe experiment, with exciting molecule to exciting state. Don't make this wave packet to oscillate. And third, it is interpretable. It agrees well with expectations of classical theory when the particle that obeys harmonic potential just oscillates as a cosine. 3 benefits. I hope that the next slide will be my favorite. Thanks much for investing time. Have a nice weekend. I will try to answer those emails that were sent to me before, and if you have more, I'll try to address.